Okay, so let's talk through this first 18.1 to 18.3. We're talking about electric charge and the electric field. We've got a kid here being an idiot. I don't know what he's doing. Actually, okay, so when he goes down the slide, right, he ends up getting charged. The electrons that he gained are trying to get away from each other because like charges repel each other. You always opposites attract, like repel. Same thing here. The electrons are moving as far away from each other as they can when they run until they run into the ends of the hair, and then the hair wants to get out. Since the hair gets charged, all the individual hairs want to run away from each other. So let's talk about the rest of this stuff. You got 18.1. Talking about static electricity and charge. I'm going to change the color. There we go. Static electricity and charge, conservation of charge. So that's our big thing. Charge is conserved. We'll talk about conductors and insulators and the difference between those. And then the first analytical part of the chapter will be in Coulombs Law. Okay, and that's calculating the force between two charges. So introduction here, we've got Ben Franklin here playing with a kite in a lightning storm with the key, and he did the thing where the kite got struck by lightning. Or even not even doing that, but just having it up high in the sky, he noticed that there was a certain charge gained, okay? And you can read this introduction, it's a little bit weird, but the idea is that there's another force here, and it's the electromagnetic force. We know the force of gravity, gm1m2 over r squared. If you have two objects, two planets with a certain mass, you know that the force of gravity between them is dependent on the distance r separating them. The further apart they are, the weaker the force. And you also know that F equals ma. So if a mass experiences a force, it will accelerate, and you can calculate how much that acceleration will be. So that's why it's important to be able to calculate what the force is, so that we can then calculate what the acceleration is going to be. So then we can make a photocopy or something, shoot ink around. Okay, so 18.1, static electricity and charge, conservation of charge. The important thing here is that electric charge is conserved. What that means, there's a couple important points here. Let's read through these. There's static electricity, that's in the winter especially when the air is drier, so humidity will carry charge away. It allows electrons to escape and jump off of you. In the winter, when the air is very dry, you hold on to that charge a lot easier. So when you're shuffling around on a carpet, you end up stealing some of the electrons from the rug, ending up in your body, and when you touch a piece of metal, it zaps you, or when you touch your friend, it zaps you. That's static electricity. Where does that excess charge come from? You're taking it from somewhere, and that's the essence of this. You cannot create or destroy charge. You merely take it from one spot and put it somewhere else. So static electricity explained by a physical quantity called electric charge. There's only two types of charge, positive and negative. That's it. Like charges repel, unlike charges attract, so opposites attract. And then the force of between the charges decreases with distance, so that's an important point. So how do we know there's only two types? We do these experiments where you rub a balloon on your head, for example, and stick the balloon to the wall, and you go, wow, it's sticking to the wall, how'd that happen? Or what we'll do in class 2, if you charge up a nylon rod or a PVC pipe or something and rub it with a cloth, you end up ripping electrons off of the cloth, or the rod ends up ripping electrons from the cloth. In one case, during that rubbing action, you end up moving charge around. So you can end up giving something a net positive charge and something a net negative charge. And then after you do that charging experiment, you see that the two rods, if you charge two cloths and two rods, the two rods are going to repel each other. So in this case, you've got a pipe hanging from a ceiling, and so that means it can spin freely. So when you bring a rod close to it, it's going to experience a force that causes it to rotate. That opposite attracts force, or the like repels force. Same thing here with the two cloths. They're going to appear to push apart from each other once they have the same charge. So that's how you can determine how many charges there are, how many iterations, and so on. Okay, so electrons are negatively charged, protons are positively charged. So that's essentially what's going on here. When you take an electron from something, you leave protons behind. So you take electrons away, you make something a net positive charge, or you put electrons on something, it becomes a net negative charge. So that's the essence here. You've got an atom, And an atom is a nucleus of protons and neutrons, so it's a net positive charge because the neutrons have no charge. And the electrons have negative charge. So if you take an electron away, now you only have 2 negative charges, and you might have 2 or 3 positive charges from the proton. So you can charge your atom up in a positive way. Of course, this is not what an atom looks like. An atom, if you had Kinnick Stadium here, and the press box up here, the nucleus would be a P on the 50-yard line, and the electrons would be orbiting out of the press box. So that's to scale what an atom really looks like. Okay, so anyway, the charge, the fundamental unit of charge of one electron, a single electron, if you could measure the charge of a single electron, is 1.6 times 10 to the minus 19 coulombs. And that's the SI unit, the coulomb, okay? 1 coulomb is a bunch of protons or a bunch of electrons, okay? So that's just how, when we calculate how much charge there is, we use the unit coulomb. But if we want to know what's the charge on one electron, we know each one is this. So if we wanted 1 coulomb, we need a bunch of electrons or protons, 6.25 times 10 to the 18th electrons. So that's 1 coulomb. Yeah. This says here, just as there is the smallest bit of an element, which is called the atom, there is the smallest bit of charge. There is no directly observed charge smaller than the charge on an electron, okay? And all observed charges are integral multiples of the electron, okay? And we'll get into a little bit here how the proton works ultimately. Okay, so we got a figure here, a Van de Graaff accelerator. Maybe you've played around with one of these things earlier in your life or at a museum or something. Inside this Van de Graaff accelerator is a belt, and the belt is just going around like that, a little motor, and every time it goes up, there's something rubbing it at the top. So you're just scraping charge, and you're depositing charge onto the sphere, and when you put your hands on it, that charge wants to get away from the other charges, so it goes down and out into your hair, and then all these things are repelling away from each other, and that's how that works. So anyway, you can tell your family how that works the next time you see one. An accelerator. Let's see, so now the ultimate thing here, when you zoom all the way in, you've got your electrons floating around your atom, and then you've got your protons and neutrons at the center of the atom, and if you zoom all the way in on a proton, you see, hey, wait a second, there's some things inside a single proton. We call those things quarks. This is a little bit of an aside here. This isn't super important, but we'll talk about this later. What makes a proton have a positive charge is that it's made of quarks that have fractional charge. And the case for the quarks that make up a proton, you have to make sure that the total charge is unit 1. And so you need a plus 2/3, plus 2/3, and then a minus 1/3 charge quark. Put those 3 together, you end up with a proton. The electron itself is structureless. It has no substructure as far as we can tell. So that is 1 negative charge, but the proton is made of 3 fractional charges. So anyway, that's just interesting aside. Okay, so the separation of charge in atoms is like we already talked about a little bit. If you have 2 objects, they have different molecular structures. Some it's more easy to take electrons from, some it's harder to take electrons from. So if you take 2 objects and rub them together, you may gain or lose electrons depending on the property of the material. And you can this is just something you have to experimentally determine really by going around rubbing a bunch of stuff. Okay, but in the process of all of this, total charge is constant no matter what. So you could move charge over to the paper or the cloth here, or you could take charge off the cloth onto the amber. Either case is fine depending on the materials, but you can't, during that rubbing, you're not just going to create charge out of nowhere, okay? You're transferring charge and giving one thing a net charge or something else. Then there's another aside here on particle physics. If you smash 2 protons together in an accelerator, you create energy, E equals mc squared. So if you have this much energy, you can end up creating mass. Delta M. And this is how we create particles in an accelerator, by creating pure energy. Anyway, that's weird. But even in those cases, charge is conserved. So I think that's all they're trying to explain here. Okay, so making connections, conservation laws. So there's a lot of conservation laws in the universe: conservation of energy, conservation of momentum, conservation of angular momentum, and conservation of charge. That's one of the other ones. Okay, so anyway, that's important. And then we've just got an example of energy creating two particles, an electron and an anti-electron. Charge before 0, charge after 0. The conservation of charge is respected, and in this case the electron and the anti-electron, they have opposite charges, so the sum of the two charges together maintains a net charge of 0. You could also annihilate an electron and a positron together and create pure energy. In that case, the total charge before and after is still 0. Okay, and then we've got a PHYS here. Click on this link here, or in the course website, it should be in line with the text. You can click on that, so you might be able to see that if you're reading this on the Canvas website. And you can just play around with that. All right, so there's two types of things, conductors and insulators. Conductors allow the free motion of electrons, so that's like wires, copper wires in your house for electricity. Insulators prevent electricity from getting out, which is why, for example, cables are wrapped in this rubber. That's an insulator. It will not allow electrons to go through the plastic into your hand. So those are the two main types of things. Like glass is another one. Glass doesn't allow charge easily through them. You're going to get conductive glass and different, dope them, but generally, like glass in your window is not going to allow charges to move through them. We're going to have a thing like this set up in class, hopefully. A demo called an electroscope, and you can determine the charge of something by looking at it. When you bring a charged element to this node here, it's going to pull negative charges up towards it, and then it's going to shift this paper down here, and it will actually change the angle, so it allows you to measure how much charge is on something. So this is just a nice little example. Electroscope is a favorite instrument in physics demonstration at student laboratories. Yes, that's correct. You will see that tomorrow. So there's two ways to charge something up. Charge something by contact or charge something by induction. Charging something by contact means you bring your hands together and rub them together, and then you're going to just physically remove charges from one surface and put it onto another. Another case is if you just bring an object close to another object, it's sort of like, you can think of charging by contact. Imagine a celebrity walking through a crowd. It's going to just grab onto all the people. They're going to follow them really close by, and they're going to, drag them along and take them out of the, let's say a celebrity's walking down the street past a coffee shop. The coffee shop door is open, so the people are going to come out of the coffee shop and be attracted to the celebrity, whereas the people who are too cool are going to stay in the coffee shop and not respond at all. So charging by induction is a little bit different. It would be like the coffee shop door is shut and locked, so as the celebrity walks by, all the folks in the coffee shop that are attracted to the celebrity are going to move towards the window, but they're not going to be able to leave, so it's more of a temporary effect. And then, so the room's going to end up separated inside the room. You're going to have people on the window that want to see the celebrity walking down, and then people over here on the other side be separated, and let's say there's a wall between them, and you could close the door. And then that would end up with, you'd break the group into two different sets, fans and non-fans, and all you had to do was put a celebrity down the hall, down the street in order to do that. If the celebrity wasn't there, then this room would be evenly mixed with fans and non-fans alike. But as soon as that celebrity gets there, boom, you end up with fans over here and non-fans over there. Same idea. This is called induction, remember, because we're not actually in contact with the fans. So this is how it works. You've got two silver spheres here. You bring a positively charged rod near, so the negative charges are going to be attracted to it, and the non-negative charges are going to be repelled by it. So they're going to move to the other side. Then if you separate this, so you pull this apart, now when you remove this positively charged thing away from it, you end up with a sphere so this whole sphere is net negative, this whole sphere is net positive. So you created a charged sphere without having to touch anything. Okay, so that's charging by induction, and that's kind of how photocopiers work when they charge up the paper, and then charges are attracted to it through that induction process. Okay, so then anyway, so this is just going through that. Here's another example, charging by induction. When you use a ground connection, what does ground do? Ground is just a way for electrons to leave. So it's an escape hatch, right? So you bring your positively charged sphere in here, you ground it, and boom, all those charges get pushed off. Then if you disconnect the ground, then you end up with a charged sphere. It's sort of the same idea. So in this first case, this guy is acting as the ground. In the second case, you don't have a second sphere. You just use the ground connection. And that's on your cable. When you plug stuff into your outlet, that big round plug in the bottom of it, that's your ground connection. So that's a way for electrons to escape. And grounds help keep electronics safer in the case of a fault or an error. It just shorts the circuit right to ground instead of going through your body to try to make you safer. So that's why it's important to not remove that or try to delete that if you're in some cases where you don't have that connection. It's safer to use that. Okay, so anyway, a couple more examples. Read through those. Positive and negative objects, depending on if it's positive, negative, whatever. It's just charging by induction. That's all this is explaining. So check your understanding. We've got here, this is doesn't look like it, but this is a faucet, and this is a stream of water coming out of it. The water is being attracted towards the charged rod here. So someone rubbed this rod and charged it up and brought it close to the water, and the water is getting bent. Okay, so you know from Newton's laws, an object in motion stays in motion, so it should fall unless acted upon by an outside force. Well, some force then is pulling this water over. What is the force? It's the electrostatic force or the electromagnetic force. So what is causing that force? We know it must be that there's a charge here and there's a charge in the water. Okay, well, if we look up a water molecule, it's H2O. It looks like this. You've got two H's and one O. Okay, and these guys are positively charged, and this one's negatively charged. Now, the cool thing about the water molecule is it's asymmetric. So these positive charges are top-heavy, and this minus charge is on the bottom. So what ends up happening is there's a polarization. So if this is a positively charged rod, then you're going to end up with something like this, and your positive charges are going to be over here, and your negative charge is going to be over here. This allows a polarization of the water. The water molecules will all flip around and try to line up, and then you end up with a net force between these two things, and you end up with a force of attraction between them. And so that's what this is explaining here. Okay, and then we've got a simulation there that you can go through. All right, 18.3, Coulombs Law. So now we're actually going to put some numbers in here, and Coulombs Law, if you've looked closely and remember the first semester of college physics, you might remember the force between two masses of gravity. This is the exact same force. Instead of G m1 m2 over r squared, we have K q1 q2 over r squared. Now remember, q1 and q2 are measured in coulombs. That's the SI unit. So whenever you do a problem, they're going to ask you, what's the, if this charge has, let's say you got 20 electrons. Well, you're going to have to convert that 20 electrons. Each one has 1.602 times 10 to the minus 19 charge coulombs on it. So you're going to multiply that by 20. That'll give you the charge in coulombs. Multiply the two together. What's the distance between them? Okay, 1 over r squared times K. K is just a number. It's a constant, a fit parameter from doing experiments, and it's about 9 times 10 to the 9 Newton meter squared per coulomb squared. This is not a number you're going to have to memorize. It's a little bit weird, but it's there just as a factor to calculate this number, this problem. So the important thing is it's a 1 over r squared law. An inverse square law is the technical term for it. So if you double the distance, you reduce the strength of the force by 4, or 2 squared, 1 over 2 squared. Okay, so how you do a problem like this, you've got one charge here, you've got another charge here. What's the force between them? Well, you know they're going to repel each other. So that's why you have an arrow here. The force from 2 on 1 is pointing away, and the force from 1 on 2 is pointing away. If one of them is minus and one of them is plus, then you're going to have the force arrows pointing towards each other, and then again you've got your 1 over r squared here. So we got an example here. Compare the force between an electron and a proton with the gravitational force between them, okay? And then they're saying that this is the average distance between, in a hydrogen atom, this distance, 5 times 10 to the minus 10 meters, or 0.05 nanometers. Okay, so to compare the distance, we first compute the electrostatic force. So now, if we want the force between two electrons, or an electron and a proton, we just use Q1, Q2 over R squared. Remember, they have the same charge. One's positive, one's negative. So you just plug that in with K and the distance squared, and you get the Coulomb force to be 8 times 10 to the minus 8 newtons. All right, so the charges are an opposite sign, so it's an attractive force. Great. Notice that when you use this law, you put the absolute value on the charges, and that way you don't have to worry about the plus or minus sign. You add that later. So in this case, if it's plus and minus, you know they're attractive, so you can make the force positive if you want. It really, it doesn't matter too much. It all depends on, if you're trying to do a vector, what direction is the force, that's where you're going to put that information back in, plus or minus, or I, J, K, or whatever the thing is. Let's see. Okay, so the Coulomb force, then we get that. Now, if we want to do the same thing with gravity, it's the same form of the equation, gm1 m2 over r squared. We're going to have to look up the mass of an electron and the mass of a proton if you don't have it memorized. Usually they're in the intro to the book, or in some appendix or something, but it's easy enough to just ask Google or Siri how much a proton weighs. Let's see. Hey Siri, what's the mass of a proton? What's the mass of a proton?
The answer I found is 1.008 atomic mass units.
Oh, geez. Hey Siri, what's the mass of a proton in kilograms?
The answer I found is 1.008 atomic mass units.
What an idiot. Okay, so don't use Siri. Usually they use Wolfram Alpha, not Wikipedia, which is a difference. Okay, so anyway, delete all of that from your memory, what just happened. All right, we've got G is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. That's our G constant. You may have to look this back up if, you don't, this isn't in this chapter of the book, for example, but here it is right here, so we don't have to look it up. Anyway, it's Newton's gravitational constant. We plug all that in, mass of the electron, mass of the proton, divided by the distance squared, and we get this. Okay, so it's also attractive force, right? Gravity pulls. So gravity is always attractive between two masses. It doesn't have a charge. So this is an attractive force. It's traditionally shown as positive, since gravitational force is always attractive. The ratio of between the two forces, then, if you divide 8 times 10 to the minus 8 and 3.61 times 10 to the minus 47, you see that the electrostatic force is about 10 to the 39 times stronger than the force of gravity. And this is what makes it so difficult to determine what's going on inside of a black hole, because the electrostatic force is so much more powerful than gravity. We can't do an experiment to probe how these forces interact with each other, because the electrostatic force overwhelms the gravitational force. It doesn't even come into play in the equations. It's such a small effect. It's such a small addition. So this is a remarkable ratio, right? So this is exactly why, by the way, that you can use a fridge magnet to pick up a paperclip, okay? Because you're defeating the gravitational force of the entire planet Earth when you lift up that paperclip using just a tiny fridge magnet, okay? So the force of gravity is exceptionally weak. I can jump up in the air and my legs can defeat the force of gravity, right? So that's just gives you an idea of how weak the electrostatic force is. Okay, so that's the end of that chapter.